Okay.
All right, my name is Matt Bauhoff. I'm a petroleum engineering professor at the University of Texas at Austin. This is our last video lecture on a series on Matlab programming. I'm going to pass it over to a PhD student of mine, Yashar Mamani, who is going to talk about some advanced programming techniques and techniques for debugging and advanced tools in Matlab. And that's the subject of our final video tutorial.
Thank you, Matt. Let me just grab this real quick. All right. Okay, so the first topic that I'm going to talk about is going to be on how to use Tock and the profiler feature of Matlab. Basically, what we want to do is we want to basically time our program and see how it's doing in terms of performance. And the simplest way of doing it is to use the commands tick and tock in pair, and between the tick and tock, you make sure that you have your code that you want to time. And I've written a little piece of code here, and we want to see how long it takes. And so if I run this, and you can press F5 to run it. Depends on the Matlab version, but let's see. Well, it didn't do that here. Let's do it one more time. Okay, so and let's suppress the rest of the code. This is a code that I've written beforehand. So Control R, by the way, comments everything out, and Control T, removes them from being comments. So like this, Control R and Control T. So if I run this now, I'm going to get the time that it takes to execute lines 4 through 15. And you can see that the elapsed time is 0.003 of a second. And all right, so that's Tock, and I'm going to talk about the profiler in a second. But what I want to talk about first is basically this demo is going to be on making sure that your code runs as fast as possible and is performing as highly as possible. And you need tools to figure out how long it takes and what are the bottlenecks of your program, so you can go ahead and change your code a little bit or use alternatives that take less time to execute. So the first thing I want to talk about is pre-allocation. And let me just delete, Control Z, by the way, is undo. And I'm just going to put these over here. So what this piece of code does is that we assign a size for the matrix. So we have a matrix, let's say 1,000 by 1,000. And maybe it's best to switch over here. So we want to construct a matrix that's 1,000 by 1,000, and this is our n, and it's going to be a tridiagonal matrix. And in the diagonal, we want to put a number. I think I'm going to put 2 everywhere on the diagonal and -1 on the sides. You see these kinds of matrices a lot when you're doing 1D simulation of a discretized domain and reservoir simulation, or in other types of finite difference modeling. You also see it in other types of modeling techniques as well. So this is just a tridiagonal matrix, and we're going to try to construct it. And I'm going to construct it in 3 different ways, and we're going to measure the time that it takes to do that. So let's switch over to the desktop again. So n is the size of my matrix. I'm going to loop through from 1 to n, and on the main diagonal I'm going to put 2. And if If I is greater than 1, then I can take I negative 1. It's not 0, and I'm going to put negative 1. This is going to be the lower diagonal, and this is going to be the upper diagonal if I is less than n, so I don't get n plus 1 here. So if I run this, and let's just clear the screen every time and clear all our variables. This is usually recommended whenever you're running a program. Make sure that I usually type 3-4 things: close all, f close all. And what these do is that CLC clears the screen, clears all your variables, your globals, your persistent variables, and all your local variables. You can specify what exact variables you want to clear, and if you want to basically, if you want to know more about a command, you can go on that command and press F1. Well, it doesn't work on the 2013 version, the newest version. If you go on a command and you press F1, a little help menu will show up. Over here, you got to go to this question mark, and you can, let's say, type clear, and you know, see how you use that and how to implement that command. Know more about the command. So I'm going to type these 3 so that I get a clean, nice workspace every time. And so we're going to run this. It takes 2.49 seconds. So I haven't defined what A is. It's sort of being defined on the fly as this loop is being executed. This is not recommended. And in fact, if I hover on this, there's an orange line at the bottom of the variable A, and it says that the size appears to be changing. And it says consider pre-allocation for speed. This is not desirable because every time the size of your matrix changes, Matlab is trying to look for more memory. So it's allocating memory as the loop runs, and this is usually really slow. So if I made the matrix a little larger, for small matrices, it may not show a lot of speed difference, but if your matrix was large enough, then you can see that over here it's still executing, and it's going to take more than a couple of seconds to execute. I'm just going to terminate it. This is definitely more than 5 seconds or 6 seconds.
Terminate it.
Control C. So you press Control C, and it just returns back to the workspace. Okay, so let's try it with pre-allocating it. How do you pre-allocate? I'm going to give all the members a 0 value. And if I put n here, it means it's going to give me a matrix. I can do that, but it's the same thing. It's a matrix that consists of n rows and n columns. But because it's a square matrix, I can just put n here and not specify the other dimension. And if I run this, you can say it took 0.15 seconds, which is a lot shorter than the 5 or 6 seconds that it was taking, and we had to terminate the program for that. Now, if you want to look at the matrix, if you want to have a feel of how the matrix looks like, you can use the spy command, and this is going to give you a matrix like that, and you can zoom into the elements. It's not going to give you provide you any information about the values of the matrix. It's just going to put a dot where you have non-zero values in your matrix. For instance, if this was a smaller one, so we can see better. And the spy command would show you where the non-zero values are. So going back, because the matrix has a lot of zeros and very few of them are non-zero, you might want to consider making it into a sparse matrix. So there's a command in Matlab called sparse, and it actually allocates less memory to the matrix. So it's a memory efficient way of working with matrices that have a lot of zeros in them. And I'm just going to cut a code here that I've written before. just a little snippet. This is how you go about defining a sparse matrix. The first entry, so first you call sparse, and the first entry is the indices of the rows where you have non-zero entries in your matrix. So this is the row index. The second one is the column index, and the third one is the values of those entries. And this is the number of rows that matrix would have, and this is the number of columns that matrix would have. Here, I just want to assign all zeros. So I don't have any element in my matrix that has a value other than 0. So I'm just going to put empties here. And this is going to give me, so it's not going to store them.
Sparse NN, couldn't I?
You could, but I don't usually do that. It's probably equivalent. It's probably equivalent. Yeah, you can, let's see. Well, yeah. You can put sparse NN here as well, number of rows and number of columns. But if you had non-zero entries, and we're going to get to that in a second. Okay, so if I run this, it's not going to be as fast as the previous one. So the previous one, let's see again how long it took. 0.16. Now, if I run this, okay, maybe if the matrix was larger, it would take a little bit longer. This took 2 seconds. Oh, out of memory. There you go. So that's a problem, and it also takes slower when you work with sparse matrices this way. So if you allocate A as a sparse matrix and then try to change it by assigning values to it, then it has to reevaluate. It basically calls, I think, the sparse command over and over again, and this is really slow. So, and it also highlights this orange line, and if you hover over it, it says this sparse interesting expression is likely to be slow. So you don't assign to a sparse matrix on the fly. You actually use a sparse command to assign to the matrix directly. All right, and that's what I'm going to talk next. All right. So instead of doing that, by the way, in order to create a section, you can type double command, percentage, and this will create. So this is nothing. It's just regular. But if it creates a cell for you, and I think that's what these are. So that creates another section for you. I don't use it all the time, but it's good for demonstration purposes and also to divide your program visually into several sections. So I'm just going to comment all of this out and talk about how you properly create sparse matrices. And we're going to time it. First, I need, in order to call the sparse command, I need to know what the column indices and the row indices of the non-zero values are. So let me just switch to the Diag Cam again. So for this sparse matrix, you have 0 values over here. And what you want to do is that for this particular matrix, you know exactly, and for most matrices that you want to create, you should know what the entries are. So here you know what the non-zero and where the non-zero entries are. So for the column, you know that you have. I'm going to so in the. There we go. The first upper diagonal line goes from. So the column indices goes from. This is the column. So there's a column 1, 2, 3. And this is the row. 1, 2, 3. And so the column for the upper diagonal goes from 2 to n, right? We're going to put double dots. It means that it goes there. And then the second, the middle diagonal goes from 1 to n. And the third diagonal, yeah, colon. And the second one goes from 1 to n minus 1. For the row, the upper diagonal, they have to correspond, right? So I did the first upper diagonal first, and then the main diagonal, and then the lower diagonal. They should correspond. So the rows, so these are the columns, column indices, and the corresponding row indices are going to be 1 to n minus 1, again 1 to n for the main diagonal, and from 2 to n for the lower diagonal. And the values should also correspond. So the upper diagonal was -1, so I'm going to is -1 times ones, which is a command that creates ones of a certain dimension. Here I want the dimension to be equal to the dimension of the rows and columns that I put here. So it's going to be n minus 1, 1. Actually, 1, and it's a row vector. And the main diagonal is 2, so 2 times 1s, and it's 1 by n. And the other one is the same exact size as the upper diagonal. Okay, so that's exactly what I've done in the code, and all right, so this is exactly the column, the row, the values. So you put them into matrices like that, and then you invoke the sparse command. You put rows in the first argument, column in the second argument, and values in the third argument, and here you give the size of the matrix. When you do that, that's how you should create sparse matrices, and you don't need to modify the value of A as you go. So
don't need to loop at all.
You don't need to loop at all. You create it in one step. Undefined. I commented this part out. So let's just uncomment this, and maybe we want to compare as well. So this is a 50,000 by 50,000 matrix, and so 2.5 seconds if you define it this way, versus 0.01 seconds if you define it in one step. And they're the same thing. So SPI A, which is the A defined, so because I overwrote it, it's the tridiagonal matrix, and it's the same thing. If I want to look at the first 10 by 10 piece of the matrix, and if I want to look at it, so this is a little bit hard to see. So the way you read this is that this is the row number, and this is the column number, and this is the value of the matrix. It doesn't show the zero values. And if you want to look at it in a more user-friendly format, you can type full. That shows you the full matrix. Here I just want to look at the first 10 by 10 block of the matrix, and it gives me this. 2's on the main diagonal, -1's on the sides. Great. So that was a lot faster. There's an even faster way of doing it. If you know of the Diag command. Usually in Matlab or any other programming language, there are multiple ways of doing the same task. And if you're familiar with different ways of, it's always better to know how to do something in more than one way, so that if it turns out to be slower or inefficient, you can switch to the other, and so on. So if you know about the Diag command, then you can create diagonal matrices. So let me first talk about the Diag command. So Diag creates a diagonal matrix, and let's switch back to the document where I can explain things a little bit better. All right, Diag. in the Diag command, all right, in the Diag command, you specify the vector that you want to put in the kth diagonal. What is the kth diagonal? If this were to be the matrix that you want to create, if this is B or A or anything, it's going to be 0 everywhere, and this is the main diagonal. K is positive here, and K is negative here, and K is 0 on the main diagonal. And it may be different from, it shouldn't be different from MATLAB version to MATLAB version, but I may be misrecalling whether it's negative over here or negative over here, but you can always check that from the help menu. So I basically I know what this vector should be. I'm going to put that vector here, and I'm going to put 1 here to create a diagonal where you have values where the upper diagonal is -1, and everywhere else it's 0. Then I can create, if I put 0 here and put the main diagonal values for the vector, I'm going to get a matrix, B prime, where my vector is on the main diagonal now, but 0 everywhere else. And same thing if I put -1 here, and the corresponding lower diagonal vector here, I'm going to get the B double prime, where I have 0 everywhere else, and this is the main diagonal, and it's also 0, but the lower diagonal is -1. You can of course put any number here you want, as long as it fits within the bounds of the matrix. Okay, so that's exactly what I've done. I create a diag. It's the same as a. I just put, I renamed the variable to a diag. You see that this is the main diagonal entries from 1 to n. The values are 2, and it's on the main diagonal, so k is 0, plus a diagonal matrix where you have -1 times 1s. It's shorter by 1, and I'm going to put it on the upper diagonal. And same thing for the lower diagonal, so k is -1 here. And if I run this, and I've enclosed it between tick and tock to see, to basically compare run times. So the first piece of code takes longer. Let's see, out of memory. Okay, I think the memory options for this particular machine are set to low, so let's decrease the... So you didn't have memory issues with the sparse command because it didn't include the 0 values. But when you're using diag, you're obviously including those values. So let's... okay, in this case, it actually took a little longer. What you can do is there's a command called Sparse Diag. It creates a diagonal matrix that's sparse. When I ran it on my machine, this was the fastest way of doing things. So I think Sparse Diag, that's the command. We can always check stuff. Diag. Yeah.
Sparse Diag S. Right?
Yeah, Sparse Diag S. And yeah, but I don't think you have control over where you want to put the diagonal. Maybe you do. But you can always extract the diagonals if specified. I'm not sure. I haven't. I've used the sparse diags command to create diagonal matrices, but I'm not sure about off-diagonal ones. So, but you can always check that. Anyways, this was just another way of doing the same task. It was faster on the machine that I ran in, but maybe this is a memory problem. Maybe that usually the runtime depends on a bunch of things. Allocation, deallocation of memory that's managed by the operating system, Matlab. All those things, it's not just CPU time. So the wall clock time, which is what TikTok measures, includes all of those things. And maybe with this machine, the memory is a little bit low, and it just takes a little bit longer to allocate these diagonal matrices. which, by the way, has to find additional memory for the 0 entries. Okay, so that's all I'm going to talk about pre-allocation and sparse arrays. The best way that I recommend doing things is using the sparse command in this format when you actually have a sparse matrix. If you don't, then don't bother with it. Okay. The next topic is going to be vectorization. And let me uncomment this part, and then just comment everything else. Control R. Okay. So the first thing I want to talk about with vectorization is masking. Matlab, and nowadays also Fortran, but mostly Matlab, has this feature where you can make use of the hyperthreading that Matlab does. Usually, I think Fortran nowadays does a lot of that too. If in MATLAB you have amazing flexibility in how you write your code. So if you don't have to write loops to perform a certain task, you can write a few liners to do the same thing but much faster. And the advantage of doing this is that the code will be much faster, much more efficient, which you want if you're writing a really complicated and very long code. But the disadvantage is that the code becomes complicated to read and also complicated to develop and code. I have gotten used to this style of programming because for the applications that I work with, I need my code to run as fast as possible, and I also like the flexibilities that are built into MATLAB itself. I can do all my post-processing. I can plot things. I can do all of those things. It's much more user-friendly. So I sort of chose the middle ground where I wrote. I know that my developing my code is a little bit more complicated, but for me it's worth it at the end. So I'm just going to teach a couple of tricks and general things that you can do with MATLAB and vectorization and running one-liner codes instead of writing loops. And you can use these in tandem and in combination to do a bunch of tasks when you're writing long codes. Okay. So the first thing is masking. Let's say, let's create A again. Let's create it over here. And I'm going to have to define N. Let's give it a not too big of a value, 10. 10 is good enough. And also, let me talk a little bit about debugging before we go into vectorization, because this is going to help us go through the rest of the lecture. So you can click on this dashed lines on the side of your editor window, and it's going to give you these red dots. And when you run, basically MATLAB is going to stop at that point. And the advantage of doing this is that you can hover on all your variables and see what their contents are. Row, column, N. And this is going to help you to find bugs and mistakes in your code much faster than if you used other techniques, or maybe used the display command or just printed stuff out on the screen. And there are other things you can do with this. If I right-clicked on this red dot, I can set a condition. For instance, if this were a loop, I can say, stop if A was equal to 2, if it were a scalar, and it would stop only then. But okay, so this is just something I wanted to mention before we go through it, because I'm going to do it a lot. So back to masking. So I just stopped the code here. If I look at A now, A is sparse, so let's look at it in a more user-friendly format. I'm going to convert it to full, and this is A. Now, what I want to do is I want to take place a 3 wherever you have a -1. So this is the line that gives me a. So I can also march with F10. I'm not sure if it's going to work with this version. Well, I guess it doesn't. This is unfortunate. Okay, we'll have to rerun it. Shift F5, break. I think this breaks. So, okay, let's clear the screen. Usually with newer versions of Matlab, you can run the program with F5 and you can march through each line with F10. But for some reason, it's not working over here. So I'm just going to run it here. And I think you can use some of these to do the same thing. So mask creates. So let's look at mask. Mask is also a sparse matrix. And if you look at it, it's going to give me, it's going to put 1s wherever your -1 is, and 0 everywhere else. So anywhere you have -1, it's going to put a 1. And if I did A mask equals 3, that's going to accomplish what I want. So if I look at A again, it's going to have 3 everywhere you had a -1. You can do this for vectors, all sorts of vectors. You can do it for matrices, and it's going to be fine. So next thing, molding. So here, in this few lines of code, I'm just going to create a vector. Well, I'm going to create a vector that's 9 by 1, and I'm going to place, the entries are going to be random. They're going to be, so rand m comma 1 creates random numbers, a vector of random numbers that's got m rows and 1 column. And when I multiply it by 9, the random numbers are going to span from 0 to 10. And over here, I'm going to say, for all the entries that are less than 3, put a -1. So this is masking, right? We just covered this. And for all the entries of A that are bigger than or equal to 3, and you have to put an and here, and that are less than 6, place a 0 in that entry, and anything that's above or equal to 6, place a 1. So I'm just creating a really random vector. And let's first look at that vector. So, and it's going to be different each time I run the code because I'm creating these random numbers that I then modify. So if I run it again, it's going to be different. Okay. Now let's create another vector. And it doesn't have to be the same size, but over here I'm going to first explain the example. So I haven't done any molding. I'm just creating here. I created one vector called A. It's got 0s, 1, and -1 for its entries. And I'm going to create another vector that's the same size. Ignore this comment. And I'm just going to take the floor of B and add 1 to it. So the values are going to be from 1 to 9, or from 1 to 10. So let's look at B. That's B, and that's my A vector. Now, I can reorder. So this was A. That's A, and this is B. I can reorder my A vector in the following way. I can say, I can use the B vector as an index vector, and I can say that take the fourth element of A, 1, 2, 3, 4, that's a -1, and place it at the top. And take the sixth element of A and place it in the second entry. So the sixth element here is 1. But it's going to keep changing because I'm using random numbers. So the way you're going to do that, the way you rearrange it or reorder it, is that you're going to say A, which was the vector of 1s and -1s and 1, B. And B is my index vector, which has to be whole numbers. It has to be non-zero. And the way I created over here, the entries were from 1 to 10. From 1 to 9, actually. Okay. All right. So let's run the code and look at C and A and B. I'm going to clear the screen. Okay, A. This is my A vector. This is my B vector. So the fifth element of A is 1, 2, 3, 4, 5. It's a 0. And again, the fifth element is 0, and the sixth element is a 0 as well. The seventh element is a 1, and you get the picture. And I'm going to place the fifth element at the top, again, the fifth element at the second, sixth element of A on the third entry. And that's my C. So if I look at C, you have 0 at the top, like you were supposed to. That's the fifth entry. This is the fifth entry. This is the sixth entry. And the sixth entry was also 0. And so on. So we just we used B as an index vector to reorder A, and we got C. The nice thing is that A and B don't have to be the same size. So B can be larger. Whatever the size of B is, that's the same size that C is going to get. So I'm just going to comment this part out, and I'm going to use this instead. Here, B has double the size, but its values are between also from 1 to 9. But it's going to be double the size. So C is going to be double the size of A. So let's run this. Let's clear the screen. This is A. It's a 1 by 9 vector. And this is not showing how big the vector is. Usually in the newer versions of Matlab it does. And B is this vector. The entries are from 1 to 9. And they're whole numbers. They have to be, because we're going to use them as indices. And C is the reordered version of A according to this. It has the same size, 18, as B. Okay? So I call this molding. And masking and molding is just some terms that I use personally, because it just looks like we're molding matrices into according to whatever index matrix or vector that we have. So with these two alone, you can manipulate arrays and vectors and matrices tremendously. You have a lot of control over them, and doing all these operations symbolically, if you're not used to it, seems a little bit difficult, but over time, when you get used to it, they really save you a lot of time. For instance, if I wanted to create the A vector, I had to loop through it, and I had to put an if statement saying that wherever the entries of A is less than 3, place a -1, and wherever they're in this interval, place a 0, and so on. I didn't need to do any of this here. I used masking here, and I created my B vector. This was really simple. I didn't do any masking over here, but the molding also comes into has a lot of use when you're doing advanced programming. So another thing that I want to talk about is membership. And this is going to get a little bit more complicated. So we have two column vectors. Let me just clear the screen again. We have two column vectors. One is A. It consists of elements of 4, 3, 6, 1, and 2. And B has also some entries in it. And here's what I want to do. I want to replace, for any member in B that is in A, the corresponding element in capital A. So capital A has the same elements as A, but with a 0.1 attached to it. So 4 is 4.1, 3 is 3.1, 6 is 6.1, and so on. A and B have the small a and capital A have the same size, and in this case they have pretty much the same entries, except this is a 0.1 attached to every number. So what I want to do is that look, for instance, at B and find the first entry in A, which is over here, the third element, and replace the third element in A, so 6.1. So this is going to be 6.1. And find 1 here, 1, place 1.1, and so on. If 10 is not over here, so I'm not gonna be able to do anything with it. So 10 is gonna be 10. Find 3 here. 3 is the second element here, and the corresponding value is 3.1. It's a simple example. It doesn't really have any use, but we just want to first of all know how do you find, without doing any loop, how do you find the members of B that are in A? And that's what the isMember command does. When you say isMember B of A, it gives you a vector. The first entry is a true false, is a Boolean array. It has ones and zeros, and wherever it's the same size as B, and for any entry in B that's in A, you have a 1, and for any entry that's not in A, you have a 0. So let's look at that real quick. So B, and I'm calling it B mask. What is A? That's A, and this is B. So 6 is in A, so you have a 1 here. 1 is in A, another 1 here. 10 is not in A, you have a 0 here, and so on. isMember also gives you another output, the second output, and those are the indices of where you had those occurrences. So, and again, it's the same size as B, and the index refers to where in small a that occurrence happened. So 6 was in the third index of A, so you get a 3 here. 1 is in the fourth place in A, and you get a 4 here. And for the other ones, you get a 0. And 10 doesn't exist, so you don't get anything there. And if I wanted to do that replacement that I was talking about, where you find the elements of B in A and go to the capital A and replace that value in there, you can do it with this. Obviously, A doesn't have to. This is just a demo example. So what I do is that I say B BD mask, which is going to shrink B. So if I do B BMS, oops, it's going to give me. So B itself is this, and BMSK is the ones that were in A. And if I put them together, it's only going to give me the entries where I have ones. So that's 6, 1, 3, 2, so on. So that's this. To this, I want to overwrite this by, I also have to shrink this. I have to, so B int, B MSK those are, again, those indices in B int that were included in A. And for those indices, those are the indices that refer to A, and A has the same size as capital A, and I'm going to assign those corresponding indices to this guy. So basically, I'm going to get, my B vector is going to look like that. I've replaced 6 by 6.1, 1 by 1.1, because 6 was included in here, and the corresponding value to that, in this case, was just 6.1. 1, I replaced it by 1.1. 1 was here, and it was over here, and the corresponding value was that. The corresponding value could be something else. It could be 2.1. And I would get the, so my B would look like that. 2.1 would appear here. So basically, this complicated example just tells you, you can shrink, if you understand how these things work, if you understand masking, and we did masking here, and we used molding all at the same time in this little line, 65. It's a little bit hard to think about it at first, but once you get used to it, you just can control your arrays and matrices very well. And okay, last thing I want to mention is that I don't recommend using isMember excessively, because it's not the fastest. Well, I personally don't use it a lot because Matlab identifies it as a bottleneck, and I'm going to show you how to do that now. So, okay. So I talked about all those things. Before I talk about global variables, I want to talk about profiling. So we used Tock. Let me just comment everything out. We don't need the vectorization stuff anymore. All right. Let's just uncomment all of this as well. Okay.
What command do you use to comment or uncomment?
Oh, I mentioned that in the very beginning. It's Control R comments it, comments everything out, whatever you select, and Control T uncomments it. Okay. So a nicer way than using Tock to see what the bottlenecks of your program are, and to say you have written a really long program and it's performing really slow, and you want to know, what part of my program is taking the most amount of time, and you want to identify those really quickly in order to either rewrite those parts if necessary, or come up with better ways of doing things. So Matlab has this really nice tool called the profiler, and you can run your code. So the code's name is Matlab demo over here. I'm just going to type Matlab. Okay. And so if I run the program, if I type my code, whatever I want to execute in here, Matlab is going to give me this statistics about what what took the longest, how much each component of my program took. So Matlab demo, if I go in there, if I click on that, it's going to show me all the lines in there and how much it took. If I want to look at it in detail, I just scroll down and see that the parts that are highlighted in dark red are the parts that took the longest, so 0.8 second over here. This piece shows that this allocation over here took really long. So, but you can also see the same thing that Tock told us. If you build your tridiagonal matrix this way, it practically doesn't take any time, a very, very small amount of time. It doesn't even show up here. So, and you can, this is really, really useful when you've written a really long code and it calls multiple functions and so on, and you just want to know what's taking so long. And you can identify those very easily with this. So that's profiling. Do we have time?
Yeah.
Yeah, okay. Next thing I want to talk about is global variables. So global variables, let me just close this. Well, actually, I'm just going to comment these out. So global variables, there we go. That's what we want. So I've written a function beforehand. Where are the files? Oh, over here, okay. So this is a very simple function that I wrote earlier. And I don't know why two editors are open. Usually in earlier versions of Matlab, they're in the same editor. Let's see if we can put them in the same one by just dragging it. Nope, it doesn't work. Anyways, use earlier versions. Not earlier versions, the latest versions. Okay, so global variable, global variables are these variables that you can access from anywhere you declare them. And this is how you declare them. You put global first, and then you put the name of the variable, and MATLAB knows at that point, wherever you put this line, that G is a global variable, and it can be changed anywhere in your code, from within a function, from outside a function, from within a script, anywhere. And this, at first, when you're a beginner in programming, might sound like the greatest idea ever, but it's actually, you have to be really cautious in using them. And general practice of programming is that you should avoid using global variables as much as possible. Typically, I personally avoid them altogether and only use them whenever I have written my really long code, and I just want to. I'm interested in one single variable somewhere in my code, and I want to know, and I just want to extract some post-processing information out of it. I just want to extract the values of a certain variable that are not important to my code as the code runs, and store it somewhere temporarily. I don't want the change to be permanent. So that's when I use global variables. Let's see how you use them, though. They can be useful in that kind of application, but generally you should avoid using them. So let's look at this simple example. You declare a global variable G for global. You can name it anything you want, and I assign a value of 1 to it. Then I've written a function called fun1. It doesn't have any input arguments, and it doesn't have any output arguments. I just call it, and it goes in, and I can put a breakpoint here. And by the way, an alternative to putting a breakpoint is to type keyboard, and it does the same thing. So let's try this now. And K means that the command has been passed to keyboard, to the user. And again, you can hover on the variables. You can see that the value of G is 1. Although I didn't pass it through the function, you can find it. And let's see if we can step through the. Yeah. So, all right. F10 and F5 were the commands I was looking for to step through the code with this breakpoints. You don't have to do that. Well, I always use shortcuts, but if you don't have them, if you got to find out what the right shortcut is, depending on the version and the settings and everything. So I rarely use these things over here. It says that it's F10, but I think I tried F10 and it doesn't work. So anyways, you can step through your code using these things. It's better to use the shortcuts though. So you can see that the value of the variable G changed to 2 because I added 1 to it. And I'm just going to display that. It's on the screen if I look at it. And then I call function 2, and function 2 is a subfunction. It's in the same file, and I can put a breakpoint there too, and it goes right there. Let's declare it. So let's go past this line, and G is 2. I add another value to it. Now G's value is 3, and if I go through it all, the value of g is 3, right? And it hasn't been destroyed. I have to clear. That's another thing about global variables. Their values persist across calls. So even if your program has finished executing, the global variable is still stored in memory. So if you want to restart your program, make sure that you've cleared all your global variables. You can do that by calling clear all, which clears all your global variables and any other types of variables like persistent or local variables. You can specify exactly what you want to clear, but clear all just clears everything. So it's good to use them. Global variables, I would say, try to avoid them as much as possible. And if you wanted to avoid it, for instance, in this case, I would not declare it global. I would, I would assign something to it, and then if I want to do exactly the same thing, I would pass g into the function. Let's bring up the function. It gets g. Now it's detecting a conflict. It's coming in through the function, and it's saying that this can't be. So we're going to put a comment there to make Matlab happy. We're going to comment out keyboard. We're going to add one to it. We're going to display g, and then we're going to pass it again to the second function. And again, a conflict. We're going to resolve that by commenting this piece out, and it's going to do the same thing. And in fact, it should be much faster than using global variables, because variables passed through the function are stored, I think it's called stack memory, and it's much faster than heap memory, which I think is what is used for global variables. So try to avoid them. Use them when things get really complicated, and you're just interested in, and your code is really long, so you have an excuse for doing that, and you're interested in something in one of the variables as a post-processing step, and the change is going to be temporary. That's when I would use them. Structures. So we talked about global variables. There's, by the way, another thing called persistent variables. And persistent variables are variables that you can save inside functions. Typically, in this function, in function 1, if I get out of the function because this guy doesn't have an output, g will be destroyed. And I will have no recollection of what g was unless I pass it out. And the function won't remember what g was either if you recall it. So if I want the function to remember what g is, I can declare it as persistent variables, and there is a conflict here. So maybe I want to, because I'm passing it through the function as well. Okay. And gt persists. What is it saying? Might be unused. That's okay. We're not interested in using it. Well, actually, let's display it. That's our way of using it, and we don't need to call the second function. Okay, g+1 display. Let's display g2, and okay. Let's add something to gt2. And I only want to assign something to g if it's empty. Initially, when you enter the function the first time, the persistent variable is empty. So if you want to assign something to it the first time and not assign to it other times you call the function, you can use the isEmpty command to see if gt is empty. And if it is, this keyboard is not cooperating. Okay. So we assign the first time the variable, and so g must accumulate. If I call it twice, let's say we pass 1 to the function. Let's uncomment this part. G is not a global variable here. I'm going to pass 1 in here, And the first time, G is going to be assigned to GT, which is going to persist through the calls. And if I call it the second time, so the first time, G is going to print 2, and GT is also going to print 2. The second time, G is going to still print 2, but GT has to print 3, because the value persists through the calls. Let's see if that happens. Oh, well. What went wrong? We can do breakpoint and... Oh, we didn't call it again. We need to call it 2 times. Fun1 G. There. And do we have clear all in the beginning? Because persistent variables, like global variables, persist even after your program terminates. So you got to make sure to clear everything. So 2, 2, this is G, this is GT, first time. This is G, sorry, I think I'm saying it the other way around. Yeah, I'm displaying GT first. So GT to G2, first time around when you call function, the fun1. Second time, GT is 3, because its value had to modify to 2 the first time, and G is still 2. Okay, that's just something. Persistent variables I do use. They're useful when you're creating really complicated variables within a function that are only used within that function and nowhere else. And creating that variable takes a lot of time, so you don't want to create, and you need to call that function a whole bunch of times, and you just want to save some time in only creating it once and then having the function remember the variable across future calls to the function. That can be efficient, but you have to make sure to erase it, and the way you erase persistent variables is you call this clear functions. Okay. That's all about global variables and persistent variables. Let's go to structures. So structures are these new types of variables. Not new. They've been around forever in different programming languages. But there are these. They're one type of variables that are very useful, actually. So anytime you're writing a program about whatever so any program that you write for a specific application has an object of interest. For instance, whenever you're writing a reservoir simulator, the object of interest will be your grids. So in reservoir simulators, you discretize your domain into a bunch of grids, and the grids can be rectangular or any other shape. And so they have geometric aspects to them. You may need to know where the vertices are, where it's located, where its centroid is. And it may have also properties like permeability and porosity and other things. And those are all attributes of the grid point, of the grid block. And instead of defining one variable for permeability, one variable for porosity, and so on, you can define a single variable that can contain all these information about any one of the grids. Or let's say you're writing a program about analyzing the grades of the students in a class, which is the example I'm going to talk about. And the object of interest in that program will be the student, because each student will have a bunch of attributes assigned to it. For instance, their name, their age, their grade or their ID, and all sorts of things. And you can work with a single variable that has all these attributes instead of having one variable for the student names, one variable for the student ages, and also if you want to write a program for banking purposes and want to handle a bunch of accounts, the object of interest is the account, which has the name of the account holder and so on. So here I'm creating that variable called student. And the way I'm creating it is invoking this command called struct. Struct is for structure, I would assume. And So this variable I'm calling it this way. So struct, these are called fields. So I'm creating this variable called student. It has 3 fields. The first field is the name, the age, and the third one is grade. And I'm not assigning any particular size to it. It's going to be an empty struct. So let's see how that looks. So if I just run that, and type student, that's what's going to show up. Okay, and now let's say, okay, so this can be an array. You can have an array of, let's say, 10 students, each of them having, their name, their age, and their grade. And let's say you have 3 students, and this is how you assign to these struct variables. So student 1, I've assigned the name Jeff, the second one Bob, and the third one Alan. You can also assign to the age and the grade of each student, like this. So you put it, by the way, you type the name of the variable, the index of, so in this case the variable student is an array of 3. And each element of that array, has 3 fields. It has age, name, and grade. And this is how you assign. If I wanted to assign for student number 1, the age field, I would put a dot between the field name and the student variable and assign 16, for instance. That's the age. And I would do the same thing for the other the other members of that array. Okay, so let's say, and I wanted to, so let's look at the array now. Let's run this again. So student is now a structure of 3 elements. If you wanted to look at the first element, you can see that the name, you got the name, you got the age, and you got the grade of the first student. And if you look at the second one, you got all these things, all the fields. You got the name, age, and the grade of the second student. Same goes for the third student. If you wanted to look at the name, just access the name of the second student, you get that array. And you can assign it to anything you want. You can assign it to, let's say, string, str. Now str is Bob. Let's say you wanted to, you had a lot of students, and you wanted to get their grades in one single step. You can plot a histogram. Let's have 50 bins, although you don't need 50 bins. You have only 3 students, and we're going to use. So one thing I have to mention before I use this. When I type student without an index and type name, or let's do grade, I don't get a vector. I get a comma-separated list of 4, 3.6, and 2. If I wanted a vector, I would enclose it between 2 brackets, which converts the comma-separated list into an array. This is the same as using the horsecat or horizontal concatenation command. Gives me the same thing. If I wanted the column vector, I would type vertcat or vertical concatenation, and I get a column vector. Now, if I wanted to look at the histogram of these guys, if I had a lot of students, I would get a complicated histogram. Here I have only 3, so I get what do I do? The grades. So you have 2, 3.6, and 4. So that's all about structures. A few more minutes?
Yeah.
Okay. Another thing so those were structures. They're very useful. I highly recommend using them when you're writing a complicated program. For instance, I do pore network modeling, and the object of interest in pore network modeling are the pores and the throats. So the pores have a bunch of geometric specifications, specs, like the volume, the radius, surface area, and all these things, the coordinate. And you can define a variable, a structure called pore that have all these things. By the way, each field itself can be a structure. So if a student had, let's say, a field called class, you can assign to class another structure that has chemistry, physics, and all sorts of other fields. So each field of a structure can itself be a structure. I'm going to talk very briefly about cell arrays. So Matlab, everything is in terms of matrices, and matrices can contain strings, characters, numbers, and Boolean, true-false variables. You can have a matrix where the entries can be mixed. You can, where the entries, the first element can be a string, the second element can be a number, and so on. And this is how you would create it. Let's say they work exactly like matrices, although there are some differences. If I want to create a vector, a row vector of 1, 2, 3, this is how I would do it. If I want to create a cell array, I would enclose it in curly brackets. And what I would get is this. So, actually, let's rename this, because I just overwrote it. So that's A. We knew that. B looks like this. If I want the first element of B, that's how I would get it. Third element, that's how I would get it. What's the use of this? Well, I can have S here, whereas I couldn't have S over here. It would throw me an error. So that's A, and this is B. And the second element of B is a string, and the first element is a number. You can initialize structures with cell arrays. For instance, I can take the first guy, and you can also define cell arrays with the function cell. And I can say 10, 1. I only need to do it for one of the fields. So this is what I would get if I ran it. Now student is a 10 by 1 structure, and I've only assigned the first 3 of them. That's all I'm going to say about cell arrays. I've used them many times in the past. They're good to know because sometimes when you're reading inputs, some commands in Matlab, whenever you're reading off of a file, they're stored in cell arrays, and you may want to know how to manipulate them. And also, if you want to store mixed information in one variable, this is certainly one way of doing it. I don't use it excessively, though, because you don't have a label for each of the entries, whereas with struct, you have a label for the entries. Okay, and the last topic I want to talk about is inline functions, or what Matlab calls anonymous functions. Typically, whenever I want to create a function, what you would do is that you open a window and you type function. You identify the inputs, fun, and the outputs. And you can, by the way, put a tab to make the program more readable, and square the values. And the dot here is just making everything the operation element-wise, so it squares all the elements of x. And if I go to the command window and I create an array, let's clear the screen, a linspace from 0 to 1, from -1 to 1 with 100 elements, and I called fun x, and I plotted it, I would get that. A faster way of doing it, usually in Matlab, if you want to test something, you don't want to open up a file and then save that file and to test something really simple. The way I would do it, for instance, if you want to do it with an... Huh? Yeah, yeah. The way I would do it is I would create an anonymous function like this. So first you put the @ symbol, and then you define your input variables n to f, and you write the expression for your function here, and that gives you that f. Now f is a function handle, and I can do the same exact thing with the plotting. And you can use the @ symbol with this, with the name of other functions in combination to get a function handle, and you can pass those function handles into other functions as input arguments. All right, so with that, I think we pretty much covered everything.
Okay, I think we're done.
I wish a Matlab version was a little bit more recent.
We're all finished here?